So we talked about the character level models. Another type of n-gram models is what's called the skip-gram model. So in that case, we skip some words between them. So for example, in some languages, it's important to identify the grammatical construction of the sentence. And this can be easier done if we look beyond the next word. So we skip the word right next to the verb, for example, to the even one word earlier. So that's called the skip-gram model. Now, as you can imagine, high-frequency words like the or any other high-frequency word will have high count in the training corpus. So the probability estimate is going to be accurate, most probably. However, low-frequency n-grams have low counts. And in that case, they will be subject to random noise. So depending on the corpus we're training on, we might get a different probability every time. So we could train on a corpus that doesn't have the word at all. In that case, we get a probability of 0. And if we go and train on another corpus that has a lot more of the words, then we get a much higher probability. So in that case, there's a lot more noise and much higher variance in the probability. So our models will perform better if we can smooth out this variance from corpus to corpus. In addition, there's always a chance that we'll be asked to evaluate a text containing an unknown or out of the vocabulary word, okay, one that never appeared in the training corpus. It would be a mistake to assign such a word a probability of 0, because then the probability of the entire sentence will be 0. Because remember, the probability of the whole sentence is just the product of the probability of the each word in the sequence. So there are different ways to do this smoothing to avoid getting a 0 probability for a given word, or to reduce the variance of a probability from one training set to another. One way is to use the Laplace rule or the Laplace smoothing, which essentially assumes a uniform prior and then says the probability, the smooth probability is 1 over n plus 2, where n is how many times you saw that word in the training. So it's a step in the right direction, but for many natural language application, it doesn't perform very well. So it essentially tells you if you haven't seen the words and your uniform prior, assumes that it's a 50-50% probability that it will come out, which is obviously, not very accurate. So another choice is what is called the back-off model, in which we start by estimating n-gram counts, but for any particular sequence that has a low or 0 count, we back off to n minus 1 grams. Okay, so we reduce a little bit the sequence. So for example, if I'm started with an n-gram of 3 or 4, and then I have a probability of 0 for that specific n-gram, I go down to an n-gram of 3 instead and see if I have a better probability. And I can even use linear interpolation in that case to calculate 3 probabilities. So probability of the unigram by itself, the probability of a bigram, and the probability of trigram, and then combine them using coefficients lambda 1, lambda 2, lambda 3, like in this equation, to get a smooth probability. So this is another way to deal with low probability n-grams. Now the parameter values lambda 1 and so on can be fixed, or they can even be trained using expectation maximization algorithm. It's also possible to have the values of lambda I depend on the counts. So for example, if we have a high count of the trigrams, then the weight of the probability of the trigram will be more. If only we have a low count, then we put a higher weight on the bigram and unigram instead than the trigram. So this problem is very important. Another way to deal with unknown words is to just say any word that appears, less than a specific cutoff percent of time in the corpus, we'll just replace it with unknown. So I start with a corpus of 100,000 words, and then I say I'm only going to use the 50,000 most frequent words in training, and the lowest 50,000 words, I'm just going to replace them with unknown symbol. Okay, so this way I don't have to worry about the probability being 0 or anything. Now, word representations. So n-gram can give us a model that accurately predicts the probability of a word sequence. So telling us, for example, that a black cat is a more likely English phrase than cat black A, because a black cat appears in about maybe 0.0000014% of trigrams in the training corpus, while cat black A doesn't appear at all. So everything that the n-gram word model knows, it learns from the counts of specific word sequences. However, it didn't really look at the structure of the sentence itself. A black cat. So that there's a noun, cat, there's an adjective before it, and that this is a common way in English to construct name phrases, is to put an adjective followed by a noun, for example. So it didn't learn any of this. Just looked at the frequency count of a black cat versus the frequency count of cat black A, and decided that a black cat is much more likely, and that's what we're going with. So consider, for example, another phrase like the brown kitten. Now, a speaker would recognize that the brown kitten is very similar grammatically to a black cat. However, our current language model, the n-gram, doesn't recognize any of this. So we would like our model to actually learn to identify this relationship between the different phrases, okay, and to use that in adjusting the probabilities, that the brown kitten actually should be high probability because it follows correct sentence structure, and it has a noun, it has an adjective, and it's correct English. So in order to do that, we could use dictionaries, but what we could instead do is to determine the part of speech and use that as features in training our model. So in a black cat, we define that black is an adjective, so we tag it as an adjective, we tag cat as a noun, and we tag a as a pronoun, and we expect our model to learn that the sequence pronoun, adjective, noun is more likely than noun, adjective, pronoun, for example, okay, in this case. So this requires us to define what's called part of speech tagging. Okay, so one basic way to categorize words then is by their part of speech, okay, which is a tag essentially like noun, verb, adjective, and so on. So parts of speech allow language model to capture generalization. such as adjective. Adjectives generally come before nouns in English. Okay, so we want our model to learn this type of generalization. Okay, and in other languages it would learn a different generalization, and so on. Okay, so it's a useful first step in many natural language processing tasks, such as question answering or translation. So hidden Markov model is a common model used for part of speech tagging. Okay, it's a generative model that says that the way to produce language is to start with one state, such as in, for example, the state for prepositions, and then make two choices. What word should be emitted and what state should come next. So the model does not consider any context other than the current part of speech state, nor does it have any idea of what the sentence is actually trying to say. So it's only looking at the structure of the sentence. It's still a useful model because it gives us the most probable sequence of tags. Okay, and we find that the tagging achieves very high accuracy, usually around 97%. Okay, so this is a weakness for the model, is that it doesn't really understand what the sentence is about. However, it allows us to do tagging with very high accuracy. Now, another way to do tagging is using logistic regression. So, as we know, in logistic regression, the weights in the model correspond to how predictive each feature is for each category. So the weight values are learned by gradient descent. For part of speech tagging, we would build about 45 different logistic regression models, so one for each part of speech, and ask each model to calculate the probability that the example word that we're currently trying to tag is a member of a given category, given the feature values for that word in its particular context. Okay, so this means that we need, for each word, we need a feature vector, and then we would feed that feature vector and ask the binary classifier or logistic regression model to tell us the probability that this word is an adjective, the probability it's a verb, and so on. So altogether, there might be a million features, but for any given word, only a few dozen would be non-zero. Okay, so let's look at an example. So for example, the set of part of speech tagging features might include if the word before is I, so that's a feature. If the word before is you, that's another feature. If the word ends with OUS, that's a feature. If it ends with LY, if it ends with UN. If 2 words ago, the word was to, and 1 word ago, there was a verb. Or 1 word ago, the word was I, and the next word is to. As you can see, we can engineer many of these features. We end up with millions of features. Does the word contain a hyphen? Does it contain a digit? All of these are true or false statements. And then, but it's going to be very sparse. Is it all uppercase? Has attribute present? Has attribute past associated with it? And so on. And then we feed that feature vector to our logistic regression and get the probability that the word is a verb, or the probability that the word is a noun, and so on. Okay, I'll see you in the next part.